All right, what's going on, you guys? Another LeetCode video today. This problem is called word search. So we're given an n by n grid of characters called board and a string word. They want us to return true if word appears in the grid. So pretty straightforward. The only maybe thing that isn't super clear is like, okay, what is a valid occurrence of word on the board, because it doesn't necessarily have to be like Scrabble, right, where it's like has to be left to right, or up top to bottom, same row or same column. Like it can. So this is a depth first search problem, right? So and you kind of realize that after seeing that the word can kind of snake around however it wants to, right? It can be right to left, it can be bottom to top, it can be multiple rows, multiple columns, as long as the cells of the word are sequentially adjacent. That's what they say. So horizontally or vertically neighboring, just not diagonally neighboring, obviously, right? So yeah, hopefully that makes sense. The premise of the problem. Let's whiteboard this. So I made a, let's see, what is this, 4x5 board, and we're going to be looking for apple in this board, right? So we're going to have to seed our depth first search at every single cell, right? So we would start up here and we would see, okay, this X is not the same as this A. So we're going to quit our depth first search and move on to the next cell. So we would look here, we'd see, okay, is this Z the same as this A? No, it's not. So we're going to keep moving on. So now we would start our depth first search here. Okay, this A is the same as this A. So we're going to start a depth first search. We need to basically know which cells we visited so far in our current depth first search. So the way we're going to do that without using any additional space is we're just going to change this cell momentarily to a hash. Until we get back to it, we'll set it back to an A, and to make sure we're not altering the board after this function is used. But we're just going to be basically marking the cells in place. So that's how we're going to handle that. So just remember that. I'm not actually going to swap this in this walkthrough because it's going to get a little tedious. But anyways, yeah, we see this A. So we're going to continue our depth first search. The first direction we're going to search, there's going to be 4 possible directions. We're going to first search down. So we search down first. Our marker will now be here at this P. Okay, it's the same letters. That's great. So we're going to search down again. Well, we see this P is not the same as the Z, right? So we're done with this direction, but not with our depth first search. We can still go other directions, right? So we would, after going down, we would try to go up, but we would see that this cell has already been visited, so we're not going to go that direction. Instead, we're going to go to the right, and then we do see that this P is the same. So we're always going to go down first. So we're going to try to go down again. We see this L is the same, and then we see this E is the same. So at this point, we would return true, and we've found the word in the board. So that would conclude the execution of the entire function. So in terms of time and space complexity, we're going to have a time complexity that is big O of m. That m is not very good. M times n, right? Because we're going to have to, so we're seeding a depth first search, right? N by n times. So because we have to start it at each cell. Now, how long could each one take in the worst case? Well, it would be 4 to the k, because where k is the length of our word. So 4 is like is the branching factor at each point of our depth first search, and then k is the number of times we have 4 decisions to make, right? So like you could also look at that 4 to the k as 4 times 4 times 4, like k times, right? And then for the space complexity, we're just going to have big O of k, because we're not going to be using any extra data structures, but the recursive call stack does require some extra space. So, and that's exactly proportional to just the length of the word, because we're never going to have a search that's path is deeper than k, right? So big O of k for the space complexity. Again, k in both of these is just going to be the length of that word we're looking for. So yeah, let's get into the code for this problem. So just give us a little bit more room here. So the first thing we want to do is just iterate over each cell in the board. So we'll just do some simple nested C-style for loops to accomplish that. So well, I is less than board at size, I plus plus, and then this nested loop. The bound is going to be different for j. We're going to take the size of the first row in the board just to get the size of every row. We can safely assume that these all have the same size. So then we're going to say, okay, if our depth first search is true, right? We can't just return DFS because that would return it even if it was false. We got to search every cell. So, right, so only if this DFS is true, we're going to return true, right? Because that indicates that we found the word. And otherwise, we'll just return false, because that means we haven't found it if we get all the way through all of those without finding the word. So let's go ahead and implement DFS as a private class method. It's going to have a Boolean return value and take a couple parameters. So the first one's going to be the position we're at in the word. Then we want the index, or the indices that tell us what cell we're at in the board. Then we want that word, and that can just be by reference. And then we also want the board by reference. So, and that is a vector of characters, also by reference. And the reference is to just tells C++, okay, we don't want this variable to make a deep copy with the function call, right? We just want to reference the same data that we're using out here, right, for board and word. So kind of like global variables. So yeah, so the first thing let's do is let's go ahead and seed this function just to complete this part of the code. So 0, it'll just literally just be I and j. 0, because we're starting at the 0, the first character in the word at the beginning of each depth first search, right? So so then word and board. So if and actually before we even do that, let's take char c and set it to board at ij. Okay, and that'll make our lives a little easier. So we do want to check if we've already visited this cell in our depth first search. So let's see if c is equal to hash. If it is, that means we've already visited this cell, right? So we'll just return false. We know we're not going to find the word here. So we also need to make sure our position is in bounds. So if the position is greater than or equal to the size of the word, or the character we're at does not equal the word at that, the character we're at in the word does not equal the character we're at in the board, right? That's also an instance where we need to return false, or a condition where we need to return false. So let's just check if we've actually found the word, right? So how do we do that? Well, if the position is equal to the final index, which would be the size of the word -1, and the character is equal to the word at that position, we know we've if we've gotten this far in the depth first search and these things are true, if the last character matches up, then we know we found the word. So we'll just return true. And I'll bunch this with this one, put this in one code block because it's pretty related. So then the next thing we want to do is we can just increment that position, right? So we're at in the word because we're going to keep going now. You know, if we're somewhere in the middle of the word, basically that's where we are now, and we want to keep searching. So we're going to increment that position. Let's go ahead and mark the board as visited. So we'll set board at ij equal to hash, and we want to do the recursion. So, but before we do our recursive calls, we want to make sure our I and j indices are staying in bounds of the board, right? So we're going to make sure I plus 1 is less than the size of the board before we make the recursive call. So if I plus 1 is less than board.size and we return true somewhere in this depth first search of our position, which we incremented, I and j, which we are incrementing I actually, so I plus 1 and j, and then word and board. So if that comes all the way back up as true, we can return true. And we want something very similar for this, for the lower bound of I, right? So to keep it in bounds, basically the other direction. So if I minus 1 is greater than or equal to 0, right? That tells us I is in bounds when we're going upwards. So I minus 1, or when we're decrementing I. So similar code again for the for incrementing j, right? Only difference here is we're comparing it with the size of the row, right? Because j corresponds to elements within a row, or just columns, right? So, and then this is going to be j plus 1, and then we have the case where we go to the left, which is j minus 1. And that's going to be, again, just greater than or equal to 0, same as the I minus 1. So this should be it for the code, almost, right? We've got to set the board back once we're coming back out of those search paths. We'll set the board back to how it was, right? We don't want to alter any, parameters that are being passed into our function, at least not permanently, right? So kind of being a little bit hacky by modifying it in place, but it gives us much better space complexity. Take an additional data structure if we wanted to store those, basically mark where we visited in a separate data structure would obviously take more space. So that's why we're doing that in place. So this is pretty much it for the code. Let's go ahead and submit. So yeah, hopefully this video helped you understand word search better. If it did, leave a like and subscribe. I'll see you guys in the next video. Peace.